Hello, my name is Elena Sigdar and I'm an exploration geologist and GIS specialist working for Regency Mines. Today I'm going to present to you the preliminary results of a phosphate-oriented ASTER targeting study of the company's phosphate exploration project located in Sudan. Here is the disclaimer. Feel free to read through it after the presentation. Regency Mines is an exploration company with interests in the UK, Australia, Papua New Guinea and Sudan. The ASTER study, which I'm going to discuss with you today, was applied to the company's phosphate exploration project in northern Sudan. This project is located within the Jebel Abyad concession and covers a vast area greater than 31,000 square kilometres. The concession area has recently been extended and the work was completed before the extension was confirmed. The project is in its early grassroots stage and the first exploration trip took place in November 2013. During the 2013 trip, the results of a preliminary ASTER study led the team to the discovery of phosphate sources at surface. For this reason, as well as the method's cost-effectiveness in efficient targeting and the difficulty of direct detection using standard geophysical techniques, it was decided to complete a more comprehensive ASTER study across the entire concession in order to further refine target areas. We acquired the ASTER data and commissioned HME Partnership to assess the seams and to look for phosphate minerals. We then analysed their results and identified ground targets. I am now going to discuss with you the ASTER remote sensing technique. I will then explain how the data was analysed and then discuss the outcomes of the study. As a brief introduction to ASTER, ASTER stands for Advanced Spaceborne Thermal Emission and Reflection Radiometer, and is a satellite sensor launched by NASA in 1999. The sensor continuously collects electromagnetic data reflected from and emitted by the Earth's surface, which is then stored in 14 bands. Each band is a wavelength range. Here is an image of the electromagnetic spectrum. On the graph, the x-axis shows the wavelength and the y-axis shows the atmospheric transmission, or electromagnetic radiation. The spectrum contains visible near-infrared data, which our eyes can detect. The ASTER sensor also has the capability to detect longer wavelengths, such as short-wave infrared and thermal infrared data. Bands 1 to 3 covers the visible near-infrared portion of the spectrum and includes visible light bands such as green and red. Bands 4 to 9 represent the short-wave infrared section and are important in differentiating rocks and minerals. Bands 10 to 14 contain thermal infrared data, which is emitted by objects at the Earth's surface, be it that this radiation is originating from the Sun. Compared to Landsat, ASTER data is stored in a greater number of bands, which enables the detection of more minerals and rock types. By analysing the bands, surface geochemistry, rock lithology and land usage can be deduced. We acquired 12 ASTER scenes covering the entire concession area and commissioned HME Partnership to assess the scenes and look for phosphate minerals in each scene. A mineral has a unique electromagnetic signature which can be searched for in an ASTER scene. For example, this graph, which has the ASTER band number on the x-axis and reflectance on the y-axis, shows the signature of the mineral glauconite. Glauconite is an iron-potassium mineral commonly associated with phosphorites. Signature characteristics such as a strong absorption dip in band 3, followed by a reflectance peak in band 5, are diagnostic for glauconite. When you look at several signatures together, you can see that some share features and have similar shapes. For example, the phosphate mineral called hydroxylapatite is represented by the blue signature on the graph. When you compare it to goethite, an iron mineral represented by the red signature, both have a steep increase in reflectance between bands 3 and 4. Similarities like these between some mineral signatures may cause false positives. During their analysis, HME Partnership searched for 19 signatures in all 12 ASTER scenes and generated 19 indices. Here are the 19 indices overlying a grayscale coloured ASTER image. Where there is colour on this image, ignoring the outline of the concession area, there is a match between the mineral signature and the ASTER image pixel. The hotter the pixel colour, the better the match between the mineral signature and the ASTER data. Regency Mines analysed their 19 indices received from HME Partnership and compared the indices with geology, geochemistry, atmospherics, hydrology, geophysics and topography to identify primary ASTER phosphate anomalies and delineate Regency Mines' ground targets. When processing ASTER scenes, potential false anomalies are always generated as a side effect. When examining the indices, care was taken to identify any potential false anomalies and separate them from more prospective targets. Another thing we took under consideration was the ASTER pixel size. The pixels that make up the ASTER image are 15 meters in diameter, and the target phosphate beds are believed to have 2 to 5 meters of vertical thickness. The target bed is therefore unlikely to be imaged by the ASTER sensor directly. We therefore, during the analysis, looked indirectly for phosphate, such as via drainage patterns. To overcome these concerns, ground verification of the anomalies and generated targets are required. As an example of the process, here is a bird's eye view of a grayscale ASTER satellite image. This image is approximately 50 kilometers wide and was captured by the ASTER sensor in 2005. Notice the brightness contrast between the bright areas located northwest of the image and the remaining dark areas which contain smaller bright shapes. When you overlay the geology, you can see the bright areas of the previous image are now blue. This area represents the Abyad limestone unit, which has the rock code of Tal. The brown area represents the middle Abyad unit and has the rock code of Tam. Tam consists dominantly of shells and siltstones. Both Tal and Tam are part of the Abyad formation, and their contact has been highlighted as prospective for phosphate deposition. The limestone is topographically high and caps the Jebel Abyad plateau. The resistive limestone plateau, which is typically 30 to 50 meters above the lower plains, is underlain by the easily weathered shells and siltstones. The weathering of the shells and siltstones in this environment causes sediment to transport down slope. Dunes are also present in the image, which is expected in this desert environment, and the orientation and migration of dune fields show a dominant wind direction towards the southwest. Seasonal drainage and wadis are also depicted in the image. They seasonally flow and transport material from the topographically high plateau onto the lower surrounding plains. Recognizing drainage and wind patterns are important in locating the source of phosphate anomalies. When you overlay the indices, you can see how certain areas are highlighted in bright pixels. For all the indices, the hotter the pixel colour, the better the match between the mineral signature and the ASTER scene. After looking at factors influencing sediment transport, we identified which anomalies were false, such as dunes and wind artefacts. It was important to identify these wind artefacts because phosphatic sediments could be transported over large distances. Once these false anomalies were filtered out, we were able to determine which anomalies were most likely prospective for phosphate. For example, the bright pixels present here are located in the drainage as descending from the plateau, whereby the potential phosphate-rich sediment has most likely been transported. The source of the anomaly is likely to be topographically higher than the anomaly itself, so when looking for the origin of the phosphates, we are looking for phosphate-rich beds that are in their original location or in situ. This is likely to be upslope from the anomaly. The reason why the anomalous pixels are not located within in situ phosphate beds closer to the plateau is because ASTER only captures surface data taken from bird's eye view. So when there are beds vertically stacked on top of each other, only the top bed is captured by the ASTER sensor. Therefore, for this particular example, the potential phosphate source, which is believed to be located upslope, is prone to erosion by wadis and other influences. The potentially eroded phosphate source rock is then transported and deposited onto the lower plains. These sediments are then captured by the ASTER sensor and results in an image similar to the one shown on the left. Using the method outlined in this presentation, the area was subdivided into 5 zones, each of which were methodically analysed in order to define primary anomalies. During the study, Regency Mines prioritised anomalous areas that had a mixture of favourable geology, multiple indices, distinctive features such as beds, and minor or no iron mineral index presence. The last point was particularly noted because some iron minerals that are common in desert weathering have a similar signature to some phosphate minerals, as I explained earlier. It was therefore important to distinguish as much as possible between areas of anomalous phosphate and anomalous iron minerals. Now that I've explained the method, I'm now going to discuss with you the application of this method in our concession area. The following slides highlight the main results for each zone. Each zone circle is approximately 45 kilometers across. The yellow polygons are primary anomalies, the orange polygons are secondary anomalies, and the solid black line represents a geological contact. In Zone 1, 4 primary anomalies were identified, some of which show the classic wind effect. This is shown by a dominant trend of brightly coloured pixels sweeping the desert landscape from northeast to southwest. This primary anomaly is particularly interesting because it is located downslope of the Tell limestone and Tam siltstone contact, and displays distinctive features which could be indicative of phosphate. In Zone 2 there are 7 primary anomalies which have many indices present and are located near favourable geology. Similar to Zone 1, the wind effects are very distinctive. Scattered pixel anomalies in the areas highlighted are false anomalies and are caused by a large dune field. In Zone 3 there are 13 primary anomalies, and in Zone 4 there are 31 primary anomalies. The yellow anomalies with vertical hatching only contain phosphate mineral indices. The iron mineral index was not present in these areas. By distinguishing anomalies that lack the iron mineral index, we can rule out potential false anomalies. In Zone 5 there are 12 primary anomalies, several of which do not display the iron mineral index. This anomaly is an example of a potential false anomaly, whereby the iron mineral index and phosphate index are both strong. They are both present because their signatures are similar to each other, and therefore will create similar results. Although at first glance this bright anomaly seems the most prospective, the coinciding iron mineral index makes us suspicious and highlights its potential to be a false anomaly. After analysing all the anomalies, 8 high-priority ground targets were delineated, as well as multiple secondary targets. From the study completed, we have determined these high-priority targets to have the greatest potential for phosphate exposures at surface. The targets fringe the geologically prospective Tell limestone and Tam siltstone contact, which supports our phosphate deposit model generated from the 2013 field trip. Samples collected from this contact displayed anomalous levels of phosphorus, which also increases our confidence in the targets generated. To conclude, the ASTER analysis has been an excellent tool for examining a vast area in an efficient and effective manner with the goal of identifying areas of phosphate prospectivity. High priority targets have been identified for ground verification, which will include mapping and sampling. Depending on the results of the ground truthing, and once we have reduced the size of the target areas, we could consider higher spectral resolution data, such as hyperspectral imagery, because it contains more bands than ASTER and therefore can capture the more subtle features of a mineral's signature. Hyperspectral imagery would reduce the number of false anomalies and improve our success rates. It may also detect the phosphate-rich beds that are typically 2 to 5 meters of vertical thickness. After potentially finding phosphorite beds of sufficient grade, subsurface delineation work across the whole plateau may take place, such as ground-penetrating radar. As the beds are subhorizontal, the potential of a deposit could be vast. We are in the process of planning our trip to verify these targets and look forward to updating you with our findings. I would like to thank HME Partnership for their hard work and for all your time and attention. If you have any queries, please feel free to contact us. We are very keen to verify the targets and we look forward to updating you with the progress of the project.